What is bottleneck in a power transmission system? It's a condition in which the power transfer capability of the power system is limited by the maximum allowable power transfer of the transmission line. A bottleneck in power transmission refers to a point in the power grid where the flow of electricity is impeded or restricted, causing inefficiencies in the distribution of power. This can occur due to a variety of reasons such as physical constraints, outdated infrastructure, or regulatory hurdles. For example, consider a scenario where a region is generating a surplus of renewable energy, but the existing transmission lines are not capable of handling the increased load. This could be due to physical constraints such as the transmission lines being too old or not having enough capacity. As a result, the excess power cannot be efficiently distributed to areas where it is needed, creating a bottleneck. In the context of energy systems, a bottleneck refers to a point where the flow of energy encounters a constraint or limitation, leading to inefficiencies or delays. Here are a couple of examples. Permitting process for renewable energy projects. The permitting process is a critical bottleneck for renewable energy projects worldwide. It involves obtaining approvals, licenses, and environmental assessments before constructing and operating renewable energy facilities. Challenges include manual processes, under-resourced agencies, complex decision-making, and a lack of digital support. These factors contribute to long lead times and delays in project implementation. Real-life solutions include streamlining permitting through central agencies as seen in the Nordics, using frameworks like environmental and social impact assessments (ESAs) as observed in India, and addressing permitting challenges in the European Union to achieve energy transition goals. Transmission constraints and grid bottlenecks. In power transmission networks, bottlenecks can occur due to limitations in transmission capacity or infrastructure. For example, if a specific transmission line has insufficient capacity to carry the electricity generated by a wind farm, it becomes a bottleneck. This constraint can lead to congestion, reduced efficiency, and delays in delivering power to consumers. Identifying and addressing these bottlenecks is crucial for ensuring a reliable and efficient energy grid. Remember, addressing bottlenecks is essential for achieving our climate goals and transitioning to a sustainable, low-carbon energy system. Examples of bottlenecks in energy systems. Fuel supply constraints. In fossil fuel-based power plants, the availability and reliability of fuel supply can be a bottleneck. For instance, natural gas. If a gas-fired power plant relies on a single pipeline for natural gas supply, any disruption or maintenance of that pipeline can lead to reduced power generation. Coal. Coal-fired plants face bottlenecks if there are delays in coal deliveries due to transportation issues or labor strikes. Energy storage limitations. Energy storage technologies such as batteries play a crucial role in integrating renewable energy sources and ensuring grid stability. However, limitations in energy storage capacity, efficiency, and cost can act as bottlenecks. For instance, battery capacity. If a grid-scale battery storage system has insufficient capacity, it may not be able to store excess renewable energy during sunny or windy periods. Charging-discharging speed. Slow charging or discharging rates can hinder the effectiveness of energy storage systems. Grid congestion. Transmission and distribution grids can become congested due to increased demand or inadequate infrastructure. Bottlenecks occur when power flows exceed the capacity of transmission lines or substations. This congestion can lead to voltage instability and reliability issues. Intermittency of renewable energy sources. While renewable energy sources like solar and wind are essential for decarbonization, their intermittency poses challenges. The inability to predict when the sun will shine or the wind will blow creates bottlenecks in grid management. Grid operators must balance supply and demand in real time. Aging infrastructure. Many power grids and substations have outdated equipment and infrastructure. Aging transformers, circuit breakers, and other components can become bottlenecks, affecting reliability and safety. Lack of interconnection. Limited interconnection between regional grids can lead to bottlenecks. For example, if excess wind power is generated in one region but cannot be efficiently transmitted to another region with high demand, it results in curtailment and wasted energy. Addressing these bottlenecks is essential for a resilient, sustainable energy system. Addressing transmission constraints and grid bottlenecks is crucial for maintaining a reliable and efficient energy system. Here are some strategies to tackle these challenges. Investment in infrastructure. Upgrade existing lines. Modernize and reinforce existing transmission lines to increase their capacity. This involves replacing aging components, improving insulation, and enhancing conductor materials. New transmission lines. Construct new transmission lines where needed to connect regions with surplus energy E.G. wind farms to areas with high demand. These interconnections reduce congestion and enhance grid reliability. Smart grid technologies. Implement smart grid solutions that enable real-time monitoring, control, and optimization of the grid. Examples include Phasor Measurement Units PMUs. These devices provide synchronized measurements of voltage and current across the grid, allowing operators to detect anomalies and respond swiftly. Advanced Metering Infrastructure AMI. Smart meters enable two-way communication between utilities and consumers, facilitating load management and demand response. Energy storage systems. Deploy grid-scale energy storage systems such as batteries, pumped hydro, or compressed air energy storage strategically. These systems can store excess energy during off-peak hours and release it during peak demand. Distributed storage. Encourage distributed storage at substations or near renewable energy sources to alleviate transmission bottlenecks. Demand-side management DSM. Encourage consumers to shift their electricity usage away from peak hours. DSM programs can include time of use TOU pricing, charging higher rates during peak times to incentivize load shifting, load curtailment, voluntary reduction of electricity consumption during critical periods. Flexible AC transmission systems FACTS. FACTS devices enhance grid stability and control. Examples include static VAR compensators SVCs. These devices regulate voltage and improve power factor. Unified Power Flow Controllers UPFCs. UPFCs control active and reactive power flow to optimize grid operation. Grid planning and coordination. Conduct comprehensive grid planning studies to identify bottlenecks and plan infrastructure upgrades. Collaborate with neighboring regions and countries to ensure seamless cross-border energy exchange. Policy and regulatory reforms. Streamline permitting processes for new transmission projects. Provide incentives for private investment in transmission infrastructure. Establish clear rules for grid access and interconnection. Renewable energy siting and integration. Carefully select locations for renewable energy projects to minimize transmission distances. Integrate renewable energy sources into the grid strategically, considering their impact on transmission capacity. A holistic approach involving technology, policy, and collaboration is essential to address transmission constraints and enhance grid resilience. Smart grids addressing bottlenecks. Smart grids play a crucial role in addressing bottlenecks within energy systems. Efficient grid operation. Smart grids coordinate the needs and capabilities of generators, grid operators, end users, and other stakeholders. By doing so, they optimize the transport of electricity from all generation sources to meet varying electricity demands. This efficient operation minimizes costs, reduces environmental impacts, and maximizes system reliability, resilience, and stability. Real-time data and analytics. Leveraging real-time data and advanced analytics, smart grids optimize power generation, transmission, and consumption. They minimize energy losses and improve overall system performance. These intelligent systems can detect faults, reroute power, and facilitate quick restoration, ensuring minimal interruptions. Identifying and resolving bottlenecks. Bottlenecks. Smart grids enhance transparency and provide a deeper understanding of the grid. By utilizing data for grid management, they can identify bottlenecks faster. Real-time solutions prevent interruptions or outages in the power supply. Smart grids enhance efficiency, reliability, and resilience while addressing critical bottlenecks in our energy systems. Role of microgrids in addressing grid bottlenecks. Microgrids play a vital role in addressing grid bottlenecks and enhancing energy system resilience. Localized power generation and distribution. Microgrids are autonomous electrical systems that generate, store, and distribute electricity within localized communities. They serve as an alternative to traditional power grids, especially in areas with unreliable or expensive electricity supply. During peak demand or grid disruptions, microgrids can supplement the main grid by seamlessly switching to on-site generation or storage. Enhanced reliability. Microgrids offer increased reliability compared to large-scale grids. When the main grid fails, a microgrid controller detects the disruption, disconnects from the utility, and activates island mode. In island mode, the microgrid continues to supply power to critical loads using its local resources. Once the utility service is restored, the microgrid reconnects to the main grid. Adaptation to changes and vulnerability. As society becomes more dependent on reliable electricity, microgrids help vulnerable areas adapt. They provide localized resilience against grid failures, extreme weather events, and other disruptions. By ensuring continuous power supply, microgrids support critical services, emergency response, and essential infrastructure. Energy poverty reduction. Microgrids can tackle energy poverty by serving remote or underserved communities. In regions where grid extension is costly or challenging, microgrids provide a lifeline for basic electricity needs. They empower communities, schools, healthcare centers, and small businesses with reliable energy access. Integration of renewable energy. Microgrids facilitate the integration of renewables such as solar and wind at a local scale. They enable efficient utilization of distributed energy resources and promote clean energy adoption. By managing intermittent sources effectively, microgrids contribute to a more sustainable energy mix. Resilience during natural disasters. During natural disasters, e.g., hurricanes, earthquakes, microgrids can operate independently. They provide essential services even when the main grid is damaged or offline. Hospitals, emergency shelters, and critical facilities benefit from microgrid resilience. Microgrids enhance grid flexibility, reliability, and sustainability, making them valuable tools for addressing bottlenecks and ensuring energy security. Preventing bottlenecks in power transmission systems involves a combination of strategic planning, system design, and operational practices. Here are some strategies that can be used. Incorporate transmission bottlenecks into energy system models. Develop a methodology to preserve transmission links that tend to represent bottlenecks in future power systems for spatially aggregated energy system models. This can help in producing time series for electricity prices similar to those recorded in the past. Identify and improve resilience. Implement a scheme to identify the transmission bottlenecks and improve the power network's resilience under extreme events. In the quick restoration stage, adjust the operating parameters of undamaged components and maximize the largest power supply LPS with limited resources. In the slow restoration stage, identify these transmission bottlenecks and further improve the LPS by expanding the capacities of these links. Standardized procedures. Create and enforce standardized procedures. A standardized system will help to eliminate errors and inconsistencies in the process. Maintain equipment. Ensure that all equipment is well maintained and up to date. Well-maintained equipment will reduce the chances of breakdowns and improve overall efficiency. Upgrade network interface cards (NICs). NICs connect devices to the network, and upgrading to NICs with faster speeds can help prevent bottlenecks. These strategies can help in preventing bottlenecks in power transmission systems, thereby improving the overall efficiency and reliability of the system. Another example could be regulatory hurdles. The permitting process for new power projects can be lengthy and complex, causing delays in the development and implementation of new infrastructure. This can create bottlenecks as existing infrastructure struggles to meet demand while new projects are delayed. In the context of the power market, a bottleneck can have significant economic impacts. It can lead to increased prices for consumers, restrict competition, and even enhance opportunities for suppliers to exploit market power. Addressing these bottlenecks requires a combination of upgrading physical infrastructure, streamlining regulatory processes, and fostering collaboration with local communities. For instance, in the Nordics, anchoring the permitting process with central agencies has helped streamline the process. Similarly, frameworks such as environmental and social impact assessments (ESAs) have expedited renewable project delivery in India. Bottlenecks in power transmission can pose significant challenges to the efficient distribution of electricity. However, with the right strategies and policies, these bottlenecks can be effectively managed and mitigated. A bottleneck in a power transmission system refers to a point in the network that limits the overall capacity and efficiency of the system. This usually happens when a part of the system is operating at its maximum capacity, preventing further improvement in the system's performance. For example, consider a scenario where a power network is hit by an extreme event, such as a natural disaster or a cyber attack. This event might cause extensive failures and sharp performance degradation in the power network. In the quick restoration stage, the operating parameters of undamaged components are adjusted to maximize the largest power supply LPS with limited resources. However, the LPS cannot be further improved, even by increasing the capacities of most transmission links. This is due to the existence of transmission bottlenecks, which operate at their capacity limits. In short, much of the electricity we use has to be transported over long distances. Progress on grid expansion, however, is slow, which means that the grid is often stretched to the limits. Grid congestion, a bottleneck in the grid, is the result of this.